Welcome to equations reducible to separable forms, first order homogeneous equations. A differential equation in standard form dy over dx equals to f of xy is homogeneous if f of tx and ty equals to f of xy. Examples: dy over dx equals to y plus x over x. Now, our f of x of y equals to y plus x over x. We want f of tx ty. This one equals to yt plus xt over xt. We can now factor out t equal in brackets y plus x. We can also factor out t. These two will cancel, remaining with y plus x over x. Since f of xy equals to f of tx ty, then this equation is homogeneous and thus can be reduced to separable forms. Example 2. Suppose we have dy over dx equals to y squared over x. Our f of x of y equals to y squared over x. Our f tx ty equals to y squared t squared over xt. Now we can factor out t. So we have t into yt over t into x. So we get yt over x. This is not the same as this. Therefore, this equation is not homogeneous and thus cannot be reduced to separable form. Example 3. Suppose we have dy over dx equals to x squared plus y over x cubed. Our f of x of y equals to x squared plus y over x cubed. Our f of tx ty is x squared t squared plus yt over x cubed t cubed. Now, we can factor out t. So we have t into x squared t plus y over t into x cubed t squared. This one is supposed to be x cubed. So we have t into x cubed t squared. This reduces to x squared t plus y over x cubed t squared. This is not the same as this. Therefore, this equation is not homogeneous and thus cannot be reduced to separable form. Now, let's solve some homogeneous equation. Example 1. Solve dy over dx equals to y plus x over x. Now, first of all, we need to show that this equation is homogeneous. Our f of x of y is given by y plus x over x. Our f of xt yt is equal to yt plus xt over xt. We can factor out t, so we have y plus x over x. This reduces to y plus x over x. Since this equation is equal to this, then this is a homogeneous equation and thus can be reduced to separable form. Now let's go ahead and solve it. Because we have dy over dx equals to y plus x over x, let's cross multiply. So we have x dy equals to y plus x dx. From this point, we need to make substitution. Let y be equal to vx. Therefore, our dy will be equal to x dv plus v dx. Let's substitute these two in this equation. So we have x times dy, but our dy is x dv plus v dx. Y is given by vx plus x dx. So this gives us x squared dv plus vx dx equals to vx dx plus x dx. We can factor out or cancel 1x so that we remain with x dv plus v dx equals to v dx plus dx. Well, we can now subtract x dv from, we can now subtract v dx from v dx. So that will give us x dv equals to dx. Divide by x, divide by x. So we have dv equals to 1 over x dx. Since we've been able to separate the variable, we can now integrate both sides to get the answer. So integral of dv equals to the integral of 1 over x dx plus, of course, the constant of integration. The integral of dv will give us v, and the integral of 1 over x dx will give us ln x, plus, of course, the constant of integration. But v From our substitution, y equals to vx, y equals to vx, therefore v equals to y over x. So we have y over x equals to ln x plus c. We can multiply all terms by x, so we have y equals to x ln x plus xc. And this is the required solution. Now, let's go to example 2. Suppose we have x squared minus 3y squared dx plus 2xy dy equals to 0. This equation is in differential form. So first of all, we need to convert it into standard form, right? So we have 2xy dy. Let's take this term to this other side. So we have minus x squared plus 3y squared dx. Now, let's divide both terms by dx. So we have 2xy dy over dx equals to, we can rewrite this one as 3y squared minus x squared. Correct. Now, we can divide by 2xy. So we have dy over dx equals to 3y squared minus x squared over 2xy. Now, this is the standard form of a differential equation. From this point, we need to show that indeed this equation is homogeneous. So our f of x of y equals to 3y squared minus x squared over 2xy. Our f of xt and yt will be equal to 3y squared t squared minus x squared t squared over 2x t yt. Now, from this, we can factor out t squared. We get 3y squared minus x squared over t squared 2xy. This cancels and reduces to 3y squared minus x squared over 2xy. Since this equation is the same as this, then this equation is homogeneous and thus can be reduced to separable form. Now, let y be equal to vx. Our dy will be equal to x dv and v dx. Now, let's substitute this in our equation. Our first equation was x squared minus 3y squared dx plus 2xy dy equals to 0. So we have x squared minus 3. Y is equal to vx. So y squared will be v squared x squared dx plus 2xy y is vx, so x times x will be x squared v. dy is the same as x dv plus v dx. And this should give us 0. Well, let's expand this. We have x squared dx minus 3 v squared x squared dx plus, let's multiply this time and this. We have 2x cubed v dv. Let's multiply this and this. We have 2x squared v squared dx equals to 0. Let's cancel x squared from all the terms. So we have dx minus 3v squared dx plus 2xv dv plus 2v squared dx equals to 0. Now, 3v squared dx and 2v squared dx are the same, so we can add them. We get dx minus v squared dx plus 2x v dv equals to 0. Now, we can take these terms to the other side, so we remain with 2x v dv equals to v squared dx minus dx. So we have 2x v dv equals to, let's factor out dx. So we have v squared minus 1 dx. Now, let's divide both sides by v squared minus 1. And at the same time, let's divide by x. Now, x and x will cancel, so we remain with 2v dv over v squared. We remain with 2v over v squared minus 1 dv equals to 1 over x dx. Since we have been able to separate the variables, we can now integrate both sides to get the answer. So the integral of 2v over v squared minus 1 dv equals to the integral of 1 over x dx plus, of course, the constant of integration. Now, for us to be able to integrate this part, we need to use the concept of u substitution. Now, let u be equal to v squared minus 1. Our du dv will be equal to 2v. Therefore, our dv is equal to du over 2v. Now, let's substitute. We have the integral of 2v over u. Our dv is the same as du over 2v equals to the integral of 1 over x dx plus constant c. 2v and 2v will cancel, so we have the integral of 1 over u du equals to the integral of 1 over x dx plus constant c. The integral of 1 over u is ln u. The integral of 1 over x is ln x plus, of course, constant c. Now, we can raise both sides of the equation to the exponent. So we have exponent ln u equals to the exponent ln u ln x plus c. Using the laws of indices, this part can be splitted into two. So we have ln exponential to the ln u equals to exponential to the ln x times exponential to the c. C is a constant. Exponential to the c is another constant. So let's just call the resultant constant a. Now, because we have exponential function and we have ln, exponential and ln will cancel, remaining with u equals to, this will give us a constant, say a, and ln and exponential will cancel, giving us x. But we need to substitute for u, and we said let v squared minus 1 be equal to u. So we need to substitute back. We have v squared minus 1 equals to ax. Now, again, we need to substitute for v. We said y equals to vx. Therefore, v equals to y over x. So in this equation, we have y squared over x squared minus 1 equals to ax. We can multiply all the terms by x squared. So we have y squared minus x squared equals to ax cubed. This is the required solution. Thank you for watching.